Hello, everyone, and thank you for attending today's webinar, New Tools for EBSD Data Collection and Analysis. Before we begin, I'd like to review a few housekeeping items. To submit questions, please enter your question in the questions pane on the right, and you hit enter to enter it. We'll try to answer any questions that come throughout the webinar. If we can't get to your question, we'll answer you later via email. If you're having issues with technical connectivity and the webinar's not showing up correctly on your screen, first try restarting your screen. If you're still having an issue, please contact us through the questions pane and we'll try to address your issue. I'd like to introduce the presenters for today's webinar, Matt Now and Dr. Will Linty. Matt is the EBSD product manager at EDAX and has a passion for EBSD and microstructural characterization. He joined TechSem Labs, known as TSL, upon graduation from the University of Utah in 1995 with a degree in material science and engineering. At TSL, Matt was part of the team that pioneered the development and commercialization of EBSD and OIM. After EDAX acquired TSL in 1999, he joined the applications group to help continue to develop EBSD as a technique and integrate structural information with chemical information collected using EDS. Within EDAX, Matt has held several roles, including product management, business development, customer and technical support, engineering, and application support and development. Matt has published over 70 papers in a variety of application areas. He greatly enjoys the opportunity to interact with scientists, engineers, and microscopists to help expand the role that EBSD plays in materials characterization. In his spare time, Matt enjoys playing golf and pondering if changing the texture of his clubs will affect his final score. Will joined EDAX as the principal software engineer in 2020. He took an interest in electron microscopy as an undergraduate at Lehigh University before completing his PhD at the University of California, Santa Barbara in Teresa Pollock's group. His graduate work included collection and quantitative analysis of multiple 3D EBSD data sets. As a postdoc in Mark DeGraff's group, he developed a spherical approach to forward model-based EBSD indexing. Now over to Matt.
Thanks, Jonathan, for the wonderful introduction, and welcome everybody. We're really excited to have this webinar today to show you some of the recent developments that are becoming available from our EBSD product line. So a quick outline of what Will and I are going to talk about. I'm going to introduce our new Velocity Ultra high-speed CMOS detector and show you some applications with that. And then I'm going to talk a little bit about the latest version of OIM Analysis, version 9. And that'll lead into Will talking about OIM Matrix and the Spherical Indexing capability. We'd also like to acknowledge Stuart Wright from EDAX and Professor Mark DeGraff from Carnegie Mellon University for a lot of their contributions to this technology. So the Velocity is our high-speed CMOS detector series, and it's a detector that's really good for routine characterization, but as we go faster and faster, it's really ideal for 3D and in-situ characterization as well, where time is of the essence. This detector, it shortens the time to results, and we'll see some examples of why that's important. It can scale to the needs of a lab, and regardless of which camera in the series, it produces high quality, accurate orientation data on a wide range of materials. So we've had this series for a few years now, and this year we've introduced the Velocity Ultra, which is the fastest EBSD detector available. It provides live indexing speeds up to 6,700 index points per second. This capability is achieved first through having an optimized CMOS sensor that's a low noise, high speed sensor that's been essentially optimized for EBSD signal and operation. The Ultra has improved effective sensitivity via more efficient data transfer. We can get the data out of the sensor into the computer faster than with earlier Velocity cameras. And we get this fastest indexing while still maintaining high quality data. It's really important to emphasize that there's not a significant trade-off going faster in terms of the quality that the detector is capable of providing. So this is just a little graph kind of giving an idea where the Ultra fits in along the product range. So we have the Pro, the Plus, the Super, and the Ultra. These multiple models allows you to meet the throughput demands of a lab. Again, there's consistent quality across all the models. The Pro goes about 2,000 frames per second, patterns per second, and then it steps up to 3,000 with the Plus, 4,500 with the Super, and the Ultra jumps up to the 6,700. So depending on the needs that are available, there are speeds that that the Ultra provides the highest speeds for the applications where speed is really the critical goal. And so this is an example. This is you'll see this particular sample is one I've used a lot because it's a very interesting microstructure. It's an additively manufactured 316 stainless steel alloy created by laser powder bed fusion technique. This is a map collected with the 6,700 indexing points per second speeds. That essentially it's about 1 million data points, and we can collect this data in less than 3 minutes. And you can see this microstructure is very interesting. There's large grains, there's small grains, a lot of different weird shapes to the grain. So it's a fun alloy to characterize. And I'm going to show you a few different ways that we do it, but it shows we can collect data from this material very quickly. But of course, we can collect data from a range of materials at these speeds, and I often term this real-world materials. These are not just nice equiaxed, nickel grains. So here's an example from a deformed nickel sample. You can see the deformation present in that orientation map here. The colors sort of vary within some of the grains. There's a tool steel here, so it's a material that has a little bit more strain and deformation retained within the grains. And then there's a rolled deformed aluminum. So you have some amount of deformation. It's a lighter element, a weaker backscattered element material. And even on this range of materials, we can still get these fastest speeds and get high quality data from these different microstructures. So one of the big things I think we see with the Velocity Ultra and with just high-speed cameras in general is we can collect data faster, and it gets us thinking about what are the new scanning strategies we need to use for this. And this is a little example here. This is from a titanium alloy, and it's looking at the same field of view but at different step sizes. So on the left, we have a 2-micron step size for about 30,000 points. In the middle, it's an 800 nanometer step size for 200,000, and on the right, it's a 300 nanometer step size for 1.3 million. And so you can see as we resolve finer and finer, the grains become a little bit more well defined. We can measure grain shape a little bit better, and the main thing we can see is with these high speeds, we can collect statistically significant data in just a few minutes. And we can start to do things like measure, the whole microstructure, texture, grain size, misorientations in a single scan, which allows us to use the SEM time more efficiently. And it changes things from when things were, an order of magnitude or an order or 2 orders of magnitude slower. We're able to more practically collect the data we want to have to describe the materials. And so where is this useful? One is something like an in-situ experiment where things are happening dynamically, and we want to be able to capture information as quickly as possible. So this is an example of a movie of watching recrystallization in a copper material. And we start with a deformed matrix, new recrystallized grains nucleate and grow. And the faster we're able to do this, either the larger area we can look at, or the finer the time slices, or the smaller the spatial resolution. And having this capability allows us to watch to say how fast do certain grain boundaries grow, and can we track that versus misorientation type. So certainly faster detectors help to enable better in situ experiments. We're also able to look at larger areas. So we call this montage mapping. This is that same sample looking at the entire 3D build plane here. This is in what's called the horizontal build direction. This is looking at basically 13 millimeters by 7 millimeters with about a 1 micron step size. And this is captured by using 25 fields horizontally versus 13 vertically for 325 total fields. We're moving them together. We stitch this image together, and it's about 60 million data points, and we collect that in roughly 2.5 hours to give us, the entire microstructure across the build piece. And what's interesting with this is that they build this in a different direction. It's the same shape of a part, but it's built in a different direction. So this is a similar map. This one took about 2 hours. It's 45 million data points, since the step size was a little bit larger, 1.5 microns. But we can see the orientations are different, and the shape of the grains are different. And so over these large field of views, we can calculate the grains. We can group together the orientations as grains and look at the grain maps here. So this is the grain map for the horizontal build. This is the grain map for the vertical build, and you can see that the grain shapes start to be a lot different in the different build directions. And this is a two-dimensional example, but with these additively manufactured materials, this is an active area of research. This is an example from Dave Roenhorst at the Naval Research Lab, where they've looked at these type of materials in 3 dimensions and looked at the grain shapes in 3 dimensions. And you can see from these images that the grain shapes are quite interesting. They're not nice equiax grains. And so, being able to collect lots of data for both 2D and 3D analysis is important. So this is just an image from one of their 3D data sets from this paper, where this is collected from automated serial sectioning, where they did 308 sections and then used a robot polishing system between each section. And of course, if you use the Velocity series and the Velocity Ultra in particular, you're able to collect that data faster for each slice. If you're able to go, 15, 20% faster than other cameras, you save significant time when you're looking at that many sections. And so 3D is another application where a high-speed Velocity Ultra will be particularly interesting. And this is an example. This is from that same partially recrystallized copper material. So we heated it up, and then we stopped midway, and we did a 3-dimensional analysis. And you can see in 3D some of the grains that are recrystallized versus the deformed microstructure. And so with these cameras, we can do larger 3D areas while still maintaining good spatial resolution. That complements the direction of modern fib system developments of plasma fibs and laser ablation fibs, where the idea is to go to larger and larger volumes. Being able to collect data helps to facilitate that type of analysis. Another example where I think using large data sets is interesting is measuring retained austenite. This is an example from a turbine blade where we're looking at a relatively large area, looking at large packets of orientation, but trying to look at very fine step size, because the retained austenite in this microstructure can be pretty small. So we want to look at large areas because it's distributed within the material, but we want to do it with a decent spatial resolution. So this is about a 30 million point data set. It took about 80 minutes to collect something like this. And if we look at the phase map, so we have the ferritic, packet materials is the majority of the material, but those blue points are the very fine austenitic grains that we're really interested in. And so with this large area collection, with this fine step size, we're able to find these regions of retained austenite. And what's interesting about this to me is that we're able to also just look at the orientations of these austenitic grains, and we can look at just those, and you can see how they form these different little colonies within the ferritic packets. We can see that there are going to be orientation relationships within one packet. There's specific austenitic orientations that are retained. And in a data set like this is really interesting because we can use some of our parent grain reconstruction software to reconstruct the austenitic microstructure based on the ferritic orientations, and then compare that to the retained austenite to confirm the performance of that algorithm. And is an example where having all that data allows us to see multiple ferritic packets, colonies, and still detect the retained austenite in each one of them. Another example where I think that the power of the high-speed ultra comes into play is something where there's a wide range of grain sizes. So this is an example from a friction stir weld in aluminum, and we're looking right along the heat affected zone of the weld here. So on the left, we have the base metal, and on the right, we have the weld nugget here, and we go through, you can see that there's a significant difference in grain size from the left to the right. And of course, whenever we're measuring grain size, we want to be able to measure, multiple points per grain to be able to at least feel like we're getting a decent representation of the grain size. But so, we have to select a step size based on some of the smaller grains that we're going to measure. So in this case, we're looking at 700 microns by 500 microns with a 250 nanometer step size. And that gives us about 7 million data points in about 20 minutes. If we look at the grain map, you'll see here, so when I show the grain map, these grains are randomly colored to show the morphology, and we can see that there's the smaller grains and the larger grains. And we can then plot out the grain size distribution from something like that. And we can assign a color to it to say, let's just do a continuous color from blue to red across that distribution. And we can see that, sure enough, the small grains and the large grains are where we think we are, but we have enough data points to be able to resolve the smallest grains statistically and then able to take this data and break it down into small and large grained regions from this sort of bimodal distribution. So again, with this, we can analyze this full field of view in one pass. We could crop and partition out things that we want, but we're able to more fully understand, or at least fully visualize the microstructural transition across this weld zone. The other thing that this complements is, of course, having a high-speed camera. We still may want to do integrated EDS, EBSD. And so we offer our Pegasus package with our Octane series EDS detectors. By combining these EDS and EBSD together, we get accurate quantitative analysis of complex materials. Again, we're expanding our capability to the widest range of materials possible. And the speed of both the Velocity detector and the Octane EDS detector allows us to get results in minutes rather than hours or days. They're both very high-speed, high-efficiency detectors. And this is just an example on the EDS side, where this shows an ideal detector in terms of how many output counts do we get versus input counts per second. And this is other detectors. We see diminishing returns as we go to higher and higher input count rates. But with the Octane Elite detector, we can get better output even at high input signals, and we're about 5 times better than other detectors. This is important because as we're going high speed, we want to make sure we have enough counts in the detector, so we have enough counts per pixel at the high acquisition speed. So we want to be able to get lots of counts in to get lots of counts out efficiently. And so this is just a graph going to show the number of input counts per second for our different detectors by detector size. So we have our limit of what other detectors can do. They become less efficient at 200,000 input counts per second. That's sort of what they're able to process. With the EDAX detectors, though, we have our Elite and Elect Plus and our Elite Elect Super, the 30 millimeter squared and 70 millimeter squared, that allow us to get more counts in and then get more counts out. And so we're 3.5 times more output data compared to other detectors. So the combined system offers better performance. And I wanted to show a little example of how we can use that. This is an example that's a martensite in a duplex steel. So we have our image quality map on the left showing the microstructure. On the right, we have our orientation map. We can measure the orientations easily enough. But if we try to differentiate the phases, it's very difficult to differentiate the ferrite and martensite. The ferrite's body-centered cubic, martensite's body-centered tetragonal. It's a slightly distorted ferritic lattice. We can differentiate the austenite from both of these phases, but there's noise between the ferrite and martensite. But we can use the EDS information present to differentiate in this alloy the ferrite from the martensite. So we can see when we do that, we get nice phase differentiation here. Once we have that phase differentiation, then we can also make sure we identify the orientations of the particular phases. So we get quantitative analysis of each phase correctly by combining the EDS and EBSD data. That all ties into what I mentioned at the beginning of, with these cameras and the Velocity Ultra in particular, we get unparalleled EBSD data quality. And so we have a number of tools available in our system that allows us to achieve the best possible results, and we have a wide range of indexing tools to do that. So we have our default triplet indexing, our Hough-based indexing, which I'll show. We have NPAR, which improves the signal to noise through local spatial averaging. We have Chi-scan, which is the integrated EDS EBSD I just showed. We have our confidence index value that says how reliable is each measurement we make. And then we have our dynamic pattern simulation tools and our faster spherical indexing. And we'll talk to those in just a couple of minutes. So again, the base of our indexing is all based on our triplet indexing, our confidence index. This is just an example on the left of why we do this. It shows near a grain boundary. That we have a red grain on top here, we have a blue grain on the bottom. When we're near a grain boundary, we can see these patterns can start to overlap. And what we want to do is be able to deconvolute that solution. So we see on the right here the image quality map at the top. We can see the grain boundary as a region of lower image quality. But we see in the orientation map that it's pretty much a step function across that boundary, even in the areas of lower quality. And we see the confidence index map shows that within the top and bottom grains, we have a high confidence. Near the grain boundary, the confidence will go down, and that goes down because the patterns are overlapping. We don't get as nice of a solution, but we still get the correct solution. And so by having this confidence index, we're able to provide a quantitative metric of indexing performance to decide what data is good and what isn't. It gives the user control. It's not a black box. And so with that, I'll start talking just a little bit about OIM analysis. Collecting the data is the first part of understanding EBSD, but we need to do something with that data. And so this is just a little schematic showing, the main things of OIM analysis so we can visualize. We have a number of different things we can do in terms of mappings and visualization. We can analyze things like orientation, misorientation, texture. I'll jump to the right. We can understand through partitioning and reporting. And then we can still, in OIM analysis now, we have our re-indexing toolbox. This is where we can take the data that's collected on the microscope and process it further. We can find additional phases, we can index better, and that will include things like the pattern simulation and spherical indexing. So what we've introduced is our next version of OIM analysis. We call it OIM analysis version 9. This is the version that will be available with Velocity Ultra. We're working to get that. It's in the testing and release phase right now internally. And why this version's exciting is, we know with the Ultra, we can collect larger and larger data sets more easily. So we've really focused on across the board speed improvements through optimized orientation math, multi-threading of some of the calculations, and improved data input-output routines. So what we see, these are up to 30 times improvement in file opening, 20 times improvement in drawing the maps, 6 times improvement in grain calculations, and it's really ideal for these larger data sets. In addition to that, we've improved our OIM Matrix module, and OIM Matrix is our pattern indexing based on the forward modeling approach that Will's going to describe. and includes the faster spherical indexing. So before I turn it over to Will, I just want to show, here's a little movie. This is with the current version of software 8.6. I'm going to open about a 4.5 million point data set. And you'll see here it starts to work, and it's going to take a little bit of time to get this all into memory. And what I want to just show you and try to entertain you for the seconds it's going to take as it loads it is, for this data set, it was, traditionally a large data set. It takes a minute to get it loaded. It's going to take a minute to create a map. So I go up here to the Quick Gem toolbar, press this to create a map, and it takes a minute to draw this map. So when we watch it, we're done. We can do everything with our current version. It just takes a minute. Whereas now, if I go to OIM 9 and I do this same data set, this optimization, you can really see the difference in terms of time to that first map. It's much, much quicker. And just to show this a little more, this is I got one more. I'm going to do the 9 million point data set. So this is twice as many data points, but it's still very, very quick. So the good news is once you start using it, you will not want to go back, because it's a very you feel the difference very nicely. So with that, I'm going to stop talking and I'm going to turn the time over to Will.
Thanks, Matt. All right, hopefully you can see my screen. So like Matt mentioned, I'm going to be talking about forward model-based indexing in the new version of analysis. I want to start by just talking about what is forward model-based indexing for people that are not familiar. So forward model-based indexing is called that because it's solving a forward problem instead of an inverse problem. So normally when you have your patterns that you're collecting on the microscope, you want to go from the observation to the underlying information of what your sample is. And all that forward model-based indexing means is that instead of trying to do that backwards problem, we instead do the forward problem that says from a given system, what would the resulting EBSD pattern be? And then use that as the basis for indexing instead of, for example, the Hough indexing approach. And the reason that this is important is because inverse problems are often mathematically ill-posed, which means that they have a lot of pitfalls. And so by doing a forward problem, we avoid that issue. Okay, so what makes well versus an ill-posed problem? Well-posed problems basically need these three factors. The solution needs to exist, it needs to be the only solution, and it needs to be stable. And basically, Hough indexing as an inverse solution has issues with all three of those because if your interplanar triplet angle is not on your lookup table, you don't have a solution. If you have a group that's not sensor symmetric, there could be multiple solutions. And the voting system is normally stable, but can have issues for certain cases. And so basically what we see is that we have challenges with Hough indexing when we have a noisy pattern, overlapping patterns, or pseudosymmetry. And so here on the right is an example showing if you have a nice pattern on the top, when you do the Hough transform, you get these peaks that we're used to seeing, but if you just put in raw noise on the bottom, you still end up getting a couple of noticeable peaks. And so this is just one of the ways that then you can have some issues going forward. So with a forward model approach, the idea is that we describe the physics of the experiment that we're doing, and that can involve sort of an arbitrary number of factors, but typically you have some source for a beam you're using to probe your sample, a description of the beam itself, a description of your sample, and that includes the physical extent of the sample, as well as all the quantities of interest. So for EBSD, we care about phase and orientation. And then after interacting with the sample, you have a modified beam coming out, and then you have a detector as well. And the idea is that you can simulate your experiment for all of the degrees of freedom that you're interested in, and then select the result that matches your observation the best. And whatever the inputs for the simulation were, that's what you say your indexed result is. And so just for sort of more concrete example, if we wanted to simulate how do we render an image, we would say you have a flash or light source, maybe a geometry describing where that source is and how the light propagates, where your sample is and its color or reflectivity, and then you can describe the scattering when the light hits your sample, and then maybe you have a sensor with some noise profile. And normally what you want to do is start with the simplest model that you can and start adding complexity until the fidelity is sufficient for whatever you're doing. And so as you can imagine, for some experiments, this can become pretty sophisticated and involved, and that means that often these approaches are significantly more computationally intensive than inverse approaches, which is why inverse approaches are used so widely. And so the question is, if it's all this extra work, why bother? And the answer is that it gives us a much better indexing result. So here's a nice example from the literature of a heavily deformed sample, and you can see that because the pattern quality is degraded by the deformation, Hough indexing is not really able to resolve all of this fine-grained region. And on the right is dictionary index, which is a forward model approach, and it's able to basically resolve all of the regions that have the finer grains. And here's another example just with a sort of a known ground truth. This is in a nickel sample showing basically the same region scanned with higher and higher camera gain. So you can see that the pattern quality gets worse and worse. And as the pattern quality degrades, so does the Hough indexing quality, while the dictionary result is robust up until the very highest noise levels. But for this one, we know that the answer is correct, so we can have even that extra confidence that we're getting the correct solution instead of just a solution. So we know that there's a benefit to doing the forward modeling, and the question is, how do we do that for EBSD? And so we are using the approach of Mark de Graaf, and basically he splits the forward modeling from a sample to an EBSD pattern into 3 parts to make it computationally tractable. First, simulation of the backscatter yield. That's this first Monte Carlo column. Then a dynamical diffraction simulation, which is the most expensive part. And then finally, simulating an individual pattern. So I'll step through each one of those just so you can understand how we go from a sample and a description of the experiment to a simulated pattern. So the Monte Carlo simulation is a standard backscatter Monte Carlo. There's a huge number of free implementations of this available if you ever want to play around with it. The main difference is that instead of just keeping the energy distribution, which is what's normally of interest in these, we have to keep instead of this 1D histogram, a 4D histogram to know for every depth in the sample and every exit direction how many electrons came out of it. So I'm showing on the bottom left here, if you integrate over the full depth and look at that 2D histogram, this shows you the exit direction for different energy bins. And because this was done with a 70-degree tilt, you can see that you get this more electrons coming out in that sort of reflection geometry. And so what we do for our model here is you assume a monochromatic source, a perfect zero width pencil beam coming in, and then an infinitely thick sample, and then you count all of the electrons that come out from that sample with stochastic scattering and say what was the deepest that they made it into the sample, and what's the direction that they left the sample, and then you just count them all perfectly. And then once we have the Monte Carlo, we use that in a dynamical simulation. So there is a simulation done separately for every energy bin. So that's what's shown down here on the left is the hemisphere in a stereographic projection of that result for different voltages. You can see as you go to lower voltages, the bands are getting wider. This uses a block wave approach, and you basically start from the depth that you got from the Monte Carlo simulation and do the block wave approach to get the diffracted intensity, and you do it for every crystal direction in a grid of directions. And then finally, to simulate the patterns, you basically just loop over all of the different simulations that you've already done and say for each pixel on the detector, what direction needs to be what exit direction from the sample hits that pixel, and then work your way back and add up for every energy bin, what is the diffracted intensity for that bin and that orientation. And so here is sort of the view for a single energy bin, and then you would add these up for the energy bins. And you essentially are using the geometry of your detector and the rotation of the crystal to position your detector on the full sphere of diffracted intensity and then crop down the detector shape. So now that we can simulate a pattern, how do we use that to actually index? And the first approach was dictionary indexing, which is a brute force solution. And basically the idea is that we, like I said in the beginning, you just simulate every possible orientation, and that gives you a so-called dictionary of orientations. So we do the forward problem for every possible orientation and then compare against all those patterns and say which one is the best match. Whatever orientation produced that match is our orientation. And so the challenge here is that to get a sufficiently high resolution, you need impractically large dictionaries. So what happens instead is we have to use a coarser dictionary and then refine the remaining, refine the orientation between those grid points. And just to show you what sort of dictionary sizes you can reach this is showing with increasing symmetry. So for a cubic material, you can already reach intractable sizes below maybe 1/2 degree. And for lower symmetry materials, it's going to be significantly worse. And so then once you have compared against every orientation in your library or dictionary, you have evaluated the forward model on these discrete grid points. So here you can see this darkest green is our true orientation, but because our grid only covers discrete points, we need to do this sub grid point refinement to really nail down the orientation. Otherwise, we wouldn't have enough resolution in our resulting scan. So the way that this is done in EMSoft is with this BOBQA algorithm, and the idea is that basically you use the points that you have already evaluated your forward model at, fit a quadratic around them, and it would be in 3 or 6 dimensions instead of 2 for the 3 degrees of orientation freedom and 3 degrees of pattern center freedom. You fit a quadratic, say where would the maximum on that quadratic be, evaluate that point next, and then keep iterating until you reach convergence. And so here you start with the bounding grid points of your dictionary and can get a sub-pixel resolution. And this lets you switch from a 1 degree or a 1/2 degree or 2 degree, whatever step size you go with, down to a continuous orientation. So on the left here, I'm showing what you were used to seeing for a Hough indexed data set. And then in the middle is if you index with the 2.5 degree spacing of a dictionary, and then don't do any refinement, you can see you get this blocky appearance because you only have discrete orientations that you're allowed to assign. And after doing a refinement, you recover the continuous orientation as expected. And so dictionary indexing gives you this robustness of forward models that I showed in the beginning. But as you can imagine, it's much more expensive because you need to simulate all of orientation space and then compare against every pattern separately. And you have this trade-off between increasing your dictionary resolution, which means that you have a finer space to search within when you're doing the refinement step. But then you have to spend less time on the refinement, but you have a bigger dictionary, or you can do a smaller dictionary, but then you have to spend more time on the refinement step. So you sort of have this classic trade-off where the time, you can't really get much better on the time no matter what you do. And there's only a certain space that's viable because at some point your dictionary gets too large to be tractable on one side, and on the other side it becomes so sparse that you don't actually find a good initial orientation. But there is some learning curve to say what are the parameters that are available, that are viable, and what's going to work for my problem. This gets you somewhere between 1 and 100 patterns per second, roughly, depending on the setup, but your symmetry, if you're using a CPU or GPU version. And it's currently available in version 8 of Analysis with the Matrix package. And you can run it just on a subset of points if you do a partition to only clean up poor points if the speed is an issue. But we'd like to be able to get the robustness of the forward model indexing with a faster approach. And so that's what the spherical harmonic indexing is for. And it's basically you do the same type of approach as dictionary indexing, but use an FFT to get a speed improvement. So to explain how it works, I'm going to use this 2D analog. So if you imagine that, like I showed before, when you are generating a pattern from the simulation in the EBSD forward model, you can imagine it as a crop on the sphere. So you rotate the sphere by your crystal orientation and then crop it with the detector geometry. And so we can, to make things easier, just look at the 2D image version of that instead of the spherical image version. So we have a translation, which would be like what our orientation is, and then a crop from the image size that we're looking at. And so if we were going to do dictionary indexing on this 2D analog, we would start with some pattern that we want to index, and we would generate all possible crops of our input image and do the dot product. And that's what I'm showing on the right here, is for each origin of the cropped image, what's the dot product between that cropped image and this one I have on the top. And you can see there's a peak. That's the shift that we have. So if I overlay the cropped image on that, on the left showing on the values of the dot products, and on the right where that corresponds to in the image, you can see, yes, this successfully finds our image, which is not surprising. The question is, can we do it faster? And the answer is yes, this is a classic problem in image processing, and you can use a Fourier transform to, instead of doing it in number of grid points squared, you can do it in this n log n, which is potentially a significant speed improvement. And basically the idea is you can rewrite a single dot product using as a convolution, and then you can use the convolution theorem for the Fourier transform to calculate all of them simultaneously. The one important note here is that you have to make sure that the mean of your image is 0. So that's what I'm showing here. With a 0 mean, we get exactly that grid of dot products that I showed before. But if you use the image as is without making the mean 0, then you're going to prefer brighter spots. So here, this is from the lighthouse, and this is from that coastline. So you basically have this issue where since your image is all positive, then it's going to just be the best fit where the reference is the brightest. So by making the mean of the image 0, we fix that problem. So the question is there an analog to that, but instead of in 2D on the sphere? And so the question is there something equivalent to the Fourier transform on the sphere? And then we can, instead of having this grid in our image, cropped image origin, we can have a grid in orientation space. And the answer is yes. It's called a spherical harmonic transform. And just like a Fourier transform uses sine and cosine, a sum of sine and cosines to represent a function, a spherical harmonic transform uses a sum of these spherical harmonic functions to represent a function on the sphere. And if you sum out to infinity, then you can represent any function. And the bandwidth, which I'll be talking about on a few slides going forward, is just how many terms do you include. So this image on the right here is showing a bandwidth of 4. So you have a degree of 4 and an order of 4. And just like there is a forward and reverse transform for Fourier transforms, there's the forward and inverse spherical harmonic transform. And like I said before, the difference is the basis function. So instead of the Fourier transform uses sines and cosines, the spherical harmonic transform uses these harmonic transforms, or the harmonic spherical harmonic functions, which have a significantly more complex form, but it's conceptually identical. And there is an exact analog to the convolution theorem. It's just the math is significantly more ugly. But the important point is down in the bottom left here, which is that it reduces the complexity from n to the 5 to n cubed log n, which is again a significant speed up. And just to show you sort of how this looks, on the left here is a cube of Euler angle space with some slices through it. I took a random function and rotated it in an arbitrary way and did this cross correlation. And you can see you get these nice delta function peaks. There's 2 because the full cube is a double cover of orientation space. But this cube is the exact analog of this 2D grid of cross correlations. And then instead of having the origin, we just have the Euler angle triple as a result. The other nice thing is that because there is, we get a discretized result, just like with the dictionary indexing, but because there's an analytic expression for the cross correlation, you can use derivative-based refinement, which is significantly more efficient than most derivative-free nonlinear optimizations. So basically the idea is that while for EBSD pattern simulation, we start with the sphere, rotate by the crystal orientation, and then crop by the detector. We're basically doing the reverse with the spherical indexing. We back project the detector onto the sphere and then compute the cross correlation between that back projected pattern and the full simulated sphere. And then you can do this harmonic refinement, like I said, with the analytic derivative, and that gets you down to machine precision. So something like 1 to the -6 degrees. That's for a bandwidth limited function, which means in practice you don't actually achieve that because you're truncating in frequency space. But it gets you much closer starting point than the dictionary potentially. And then even though there's a lot of complicated math, at the end, it's just a button, but it's very helpful to understand what's going on behind that button. So this has been implemented in, oops, sorry about that. This has been implemented in the new version of analysis that's coming out, and it's a GPU implementation, so it's very fast. And just to show that it works, here's that same data set again, and you can see that if you use a low bandwidth, so you're using not very many terms in frequency space to capture the spherical functions, then you get a better result than Hough indexing, but not as good as the dictionary. But as you increase in bandwidth, eventually you get as good of a result as the dictionary indexing. You get confidence index for Hough-based indexing. There is a confidence metric. It's just what was the spherical cross correlation, and it is strongly correlated with image quality. So you can use them in very similar way. And just some vocabulary, because this is still a relatively new technique. There's lots of potential confusion between what people are calling things. So when people say dictionary indexing, they actually mean this two-step process of doing the brute force template matching and then subsequently doing the subgrid refinement. And spherical indexing, it's the same thing. First, you find the grid point, and then you refine between the grid points. And that first step for each of them is basically mathematically equivalent if you can, to the approximation that you're correctly able to capture your function with the spherical harmonic transform. And the real space refinement part, which is the second item in the dictionary indexing, is useful on its own as a standalone technique. So you can start from a Hough orientation and refine, or you can use it from the result of the spherical indexing and do an additional refinement to get the same level of robustness. The important thing is just that you start your search close enough to the true answer for it to work. So now that we've gone through all of the detail of how it works, we can see what does it look like on more data sets. So here is, I'll just show a couple of comparisons of Hough versus spherical. The nice thing is that while dictionary indexing, you have to generate the dictionary and there's a relatively steep learning curve. For spherical indexing, once you have that simulation, you basically just press go and you get this big improvement in your results. So here is a hot rolled material, so high deformation, and you can see a big improvement, especially near grain boundaries, because more robust to overlap patterns, because it's a forward instead of an inverse problem. Here's the same thing on the left, Hough with image quality is the gray, and on the right with the spherical confidence index. Here's a large area scan. You can, unlike for dictionary indexing, you use one pattern center to generate your whole dictionary. For spherical indexing, you can use an arbitrary pattern center for every pixel. And so that means you can get these really nice flat results over large scans, even though you have a pattern center shift. It has strong phase discrimination. So this is showing two-phase steel, and you can see that in addition to indexing a lot more of the noise points into good orientations, there's much better phase discrimination than with the Hough indexing. And this is the same sample, but with a faster collection speed. So there's basically very few grains that are recovered with the Hough, and the spherical result is noisy, but significantly improved. And then because it's an analysis, you can use all of the existing image processing tools that are in there, just like you would for Hough indexing. So here on the top right is the raw Hough indexed, which is completely unusable. If you do NPAR and Hough, you can get some result, but the combination of NPAR and spherical gives you a really nice result. There's still a little bit of noise in there, but it's quite good, and compared to the starting point, a dramatic improvement. And this is the same thing on that nickel data set, showing that you can do spherical on the raw patterns to get a good improvement, but if you do spherical plus NPAR, the result is almost perfect. You basically just lose a couple of the finest twins. So here is the low gain scan, for example. So this very fine purple twin You can sort of see it here, and since NPAR does the spatial averaging, you lose it there. And the other thing I wanted to show is that even if you have good results with Hough indexing, there's better precision with the spherical indexing. So on the left is Hough. In the center is just the first half of the spherical indexing, no refinement, just giving you the that blocky grid, the individual grid point discretized orientations. And on the right is after refinement. And the bottom is showing kernel average misorientation. And you can see that the noise threshold is much lower in the refined spherical result than in the Hough result. So we have less orientation noise, better precision. And then some practical considerations. There is basically one user parameter in spherical indexing. It's this bandwidth, which again is how far out in frequency space do you go to capture the spherical function. So I'm showing on the bottom right here, sort of if you take your pattern back projected on the sphere, do the band pass with that bandwidth, and then get out the resulting pattern, you can see that as you go higher in bandwidth, you more accurately capture the original pattern. Practically below something in around like the 40 to 50 bandwidth, you don't have enough resolution to index successfully. And then once you get to 250 or 300, you start running into slow pattern speed, and eventually there's not really a significant improvement to the index and result anyway. So in terms of speed, this is all on my laptop with a decent discrete graphics card, the bandwidth, and you can see that as you increase the bandwidth, it's basically exactly equivalent to increasing the dictionary size, and the speed accordingly drops off. But you can get speeds faster than our current Hough implementation at moderate bandwidths. And then if you're looking to sort of be ready to use the software when it comes out soon, you'll need a GPU. It needs to be an NVIDIA card because it's written in CUDA. In terms of picking one, you can basically pick a budget. I'm showing this data from a graphics card benchmark site. You can use a consumer card, any consumer card. The more you spend, the more you'll get, but there is diminishing returns at some point. For reference, the card I showed on the previous slide has a benchmark score of 8,000, and I found that the indexing speed should scale roughly with that benchmark speed. So, for example, this RTX 3070 would be about 3 times faster, or something about 15,000 patterns per second on that first bandwidth that I showed. So probably you're looking at to get something that's usable, it's probably going to be a $200 to $300 card, and these are sort of the ones that have the best price performance ratio. And so with that, I will be happy to take any questions, and from myself or Matt.
Yeah. Thanks, Will. Great job. I have some questions in. I'll answer some, and then there's one I'll probably at least pass to you. So the first question that came in is, when will OIM version 9 be available? We're aiming to have that. We're basically transitioning into testing, so we're hoping to be basically available the first of the year in that sort of time frame. There was another question regarding the high-speed camera of what's the beam current required for those 6,000 plus patterns per second. It's about the same right now as we need for the Velocity Super at 4,500. Is right in the 20-ish nanoamps of beam current. That's to get that's a benchmark speed to get the speeds with the 99% indexing success rate. So that's where the higher efficiency of the new camera comes in. We can get faster speeds at the same beam currents. And then there's another question here. With NPAR reindexing, do you expect the grain boundary texture to change significantly? And it says, to explain, NPAR averages neighboring patterns. So I don't expect the grain boundary texture to change significantly because it's going to be averaging essentially one side of a grain or the other. So those two orientations, I think, will still converge at the boundary. Essentially that may change the size slightly. Where that may not be true is something like a fine lamella grain with a large enough step size that if you were only getting a point or so along the width of a narrow grain, then that we've seen examples where that grain is lost with NPAR, and that would change the grain boundary texture. Generally, I don't think it will change it significantly, but it would depend on the density of that. But certainly,
I'm just going to chime in that in that case, you really need to be using a finer step size anyway.
That's what I was going to say too. So there's one more question here, and Will, I'm going to start answering it, and I'll let you follow up from a refinement point of view. But it's, can you comment on the speed, binning, precision trade-offs for the camera? Can you bin less for the faster cameras and get better precision at similar speeds to the slower cameras? And so, our speeds now, we're getting patterns 120 by 120 pixels-ish at the highest speeds. That resolution ties in well with our default Hough. We can go to less binning to say get 240 by 240-ish pixel patterns, and we get that at a rate of more 1,000, 1,200 speeds. I usually don't see a huge improvement though in precision, and there's two reasons for that. One is the tweaking of the Hough, getting the Hough optimized for the best band detection is a little trickier as the number of pixels go up. We typically bin the pattern down to 100 by 100 pixels for performance, and when we go to higher ones, it's I don't necessarily think we find the lines better, and also the way that our standard triplet indexing works. It does an orientation averaging of the different triplets. So for both the higher and lower binning settings, they still will have an inherent averaging that I think both precisions are relatively similar, not a huge improvement from one to the other. But I think where the precision possibilities come in at any speeds will be with the refinement. So, Will, maybe you could comment on that and how that.
Yeah. So I think traditionally EBSD detectors have had a significant number of pixels compared to the number of degrees of freedom. Ultimately, there's 6 degrees of freedom in your pattern that you're indexing, 3 for the pattern center and 3 for the orientation. So if you have an 8 by 8 pixel image, you have 64 pixels for 3 degrees of freedom. Obviously, they're not fully independent. But this is one of the areas where having a forward model and the ability to simulate patterns can help you actually start answering this kind of question quantitatively. So I've done simulated experiments where I say, for example, take a nickel master pattern, simulate what do the patterns look like for decreasing detector size from say 512 squared all the way down to a 4x4 detector in terms of that level of heavy binning, but covering the same solid angle. And I found that you're not going to start losing precision until with a forward model approach, you're not going to start losing angular precision in a meaningful sense until below something like 16 or 32 squared detector. And I'm able to reliably index down to an 8 by 8 pixel detector easily. 4 by 4 pixel is where things start to break down. So really what you need to do is look at the solid angle of your pixel, and that's going to tell you. So yes, theoretically, as you go from a 512 by 512 to a 256 by 256, you are cutting the absolute angular precision that you could theoretically achieve in half, but in practice, the numerical error, it gives you a floor, and you don't start running into that floor until below something like 64 or 32 squared patterns. You can, I found that with the spherical indexing, I can get something like a 10th or a 20th of a pixel angular precision in simulated experiments, which for a 64 by 64 detector is something like 1,000th of a degree. So the difference between binning is practically not going to make a big difference for forward model indexing. Hopefully that's a useful answer.
All right, we have another question, Will, that's will be good for you. It's do multiple phases, and in this particular question for like geological type phases, significantly slow down the forward model indexing methods?
Yeah, so basically, just like with Hough indexing, time is going to be linear in the number of samples that you index against. So if you have 10 phases, it's going to take 10 times longer. The one caveat for that is that if you have a known pseudosymmetry or orientation relationship between the phases, you could do the initial indexing against a single phase, and then you could go back and do just the real space refinement on the individual phases and then that part would be 10 times slower if you have 10 phases, but that's not the bulk of the time would be on the initial indexing. And so the answer is yes, in theory, the more phases you add, the longer it will take, but there is sometimes ways to mitigate that.
And part of that, we can use the EDS to still parse down the phases.
Of course, yeah. Or you could, if you could create a partition in analysis, then you could index one partition only against 2 phases and another partition against a different set of phases. So the answer is yes in the worst case scenario.
Yeah. And then we're to wrap it up, we got one more question, and it will be a very hand-wavy answer. It's essentially regarding OIM version 9 of the upgrading paths. That will be announced as we get closer to the launching of that product. There'll be some more details that are available. We're not really prepared to say exactly what the paths are from different versions, but that will be information that will be available to us. So with that, we'd like to thank everyone for attending. Thanks, Will, and thanks, Jonathan, for setting this up, and we appreciate your attention.